my name is Roy Simpson. I'm a professor of mathematics at Columbus College in Sacramento, California. And this is a lecture, not really much of a lecture, but a proof in differential calculus for the limit as x approaches a of the nth power of a function is equal to the nth power of the limit. One thing you have to assume here is that the limit for the function exists, and it's a finite number. That's important for all limit proofs. In fact, for all limit problems. To be able to split a limit into two different limits, or in this case, to take something outside of a limit, you're assuming that that function has a limit that exists. So that's a very important point to make. Couple prerequisites, or a few prerequisites. You have to have an idea of what a limit actually is. You should know how to do a proof by induction. If you don't, I will cover that here. Finally, we're going to use one of the limit laws that are kind of the basis for all the future limit laws. The limit law we're going to use here is that the limit as x approaches a of the product of two functions is equal to the product of their limits. In other words, it's equal to the limit of the first times the limit of the second. Now again, that limit law right there is true if and only if the limit actually exists for each of these. So this limit right here is finite, and this limit right here is finite. Otherwise, we couldn't have split that. That's a very important point, again, that we must make. Now, before I get too far into doing this, I want to just remind you of what a proof by induction is, or maybe introduce you to a proof by induction. It essentially is like a domino proof. So imagine a group of dominoes that are stacked up next to each other. Okay, and maybe I'll pause this so I can write a bunch of them. And the way proof by induction works is that we're going to knock that first domino over. So let me show that action. I'm going to start knocking this over. Now, I want to show that I can actually knock that domino over. So the first thing we're going to do is we're going to show that we can knock that first domino over. After we've shown that the first domino can be knocked over, what we're going to do is, instead of seeing what happens once we start tilting that first domino, we're going to walk down the line quite a ways. So just imagine a very long line of dominoes. We're going to go to some domino later on, like this one right here. We'll call that the kth domino. Okay. And what we're going to do is assume that that one will eventually start falling. So let me write that down. Now this assumption is just that it will eventually be knocked over. So we don't know what happened prior to it other than the fact that we pushed the first domino. But we're saying we're going to assume that eventually this kth domino is going to start falling. Okay, and maybe it's because all the other dominoes are knocking into it. Okay, what we want to show is that because that kth domino is falling, the k plus first one must also fall. In other words, we go to the k plus first domino here, which is this one right here. We want to show that because the kth domino is falling, the k plus first one has to fall as well. And if we can say that, if we can say, okay, well, therefore the k plus first domino must also fall, that means that since we kept k very arbitrary, we didn't actually tell you what k was. K could have been 2, right? That means the third one is going to fall. K could have been 3, which means the fourth one is going to fall. Which basically means that no matter where we look, the next domino is always going to fall if this red domino right here is falling. So we have the red domino that we assume is going to fall, and we want to show that it's going to knock over the next domino, that green domino. I'll go ahead and highlight that in green. We want to show that it's going to knock over that green domino. Okay. By the way, one last little piece before we get into the actual proof here. This second little bit is called the induction hypothesis, and that's just a fancy name or term for the fact that we're assuming that that kth domino is going to fall. Okay. So let's go ahead and prove our theorem, the one that we are working with here. We're going to prove this using induction. So there's our claim. The limit as x approaches a of the nth power of our function is equal to the nth power of the limit. So here's our proof. think of dominoes here. We're going to show that it works for the first domino. In other words, show it works for n equals 1. Since we're dealing with n's here, so we're going to say, well, let's see that it works for n equals 1. Well, let's see. This is just showing that we can push the first domino, that it actually will work for the first domino. So the limit as x approaches a of f of x to the, instead of n, I'm going to write the first. Let's see, what's a better way to write that? Well, without looking at our proof here, it's just a better way to write that is the limit as x approaches a of f of x. And of course, a fancy way of writing and we know, by the way, before I continue, we know that this limit exists and it's finite. That's a reality that we face when we do limit laws, is that this limit must exist and be finite. Well, since this is just some finite number, it's the same thing as saying the limit as x approaches a of f of x being raised to the first power. Aha! So if I replace these n's with 1, it totally is true. So that first domino will definitely start falling. Now we'll just state the induction hypothesis, which is that we're going to go down the line a little bit, and we're going to assume that it works for k. Assume it works for some k later on, so for some n equals k, which basically means that the limit as x approaches a of the quantity f of x raised to the k power, we're assuming that that is actually going to turn into the kth power of the limit. It might be a bad assumption, but we're going to just find out in a moment that's not a bad assumption. Okay, but right now we're just assuming that it can happen. So we made our assumption. I'll put a little green check mark there. That's our induction hypothesis. That doesn't look green to me. Oh, that looks black. Let me change that to green. All right. Let's turn the page and create the last bit of this. So now the third step, since we've shown it's true, or since we've assumed it's true for n equals k, let's show it works for the next one in the line. In other words, n equals k plus 1. So that is, we want to show, that's what WTS means. We want to show that the limit as x approaches a of the quantity of f of x raised to the k plus first is equal to the k plus first power of the limit. That's what we want to show. We haven't shown it yet, but that's where we want to go. And it's a great idea to always, when you're doing a proof, kind of state where you want to go. It helps you out, trust me. So start on this left-hand side, and hopefully we can manipulate this to turn into the right-hand side. So we have the left-hand side there, the limit as x approaches a of the quantity of f of x to the k plus 1 power. Now, without splitting the limit yet, I'm going to just rewrite that in fancier notation. I'm going to say, well, you know, that looks like the product of f of x to the kth power times, well, f of x to the first power. If you multiply these two functions, one to the kth and one to the first, you'll get that function to the k plus first power on the inside. So that's nothing. I haven't done anything outside. I haven't split this limit or anything like that. However, I am about to take advantage of one of the prerequisites that I've mentioned here. Remember back here at the prerequisite, I said if you have the product of two functions within a limit, and both of those limits exist, then you can split this to the limit of the first times the limit of the second. And one thing we've said back here is that, first of all, the limit as x approaches a of f, that exists. That's the assumption with the entire proof, is that the limit as x approaches a of f itself exists. And we've assumed, back on this previous page, we've assumed that the limit as x approaches a of the function to the kth power is equal to the kth power of the limit, which means that that limit also exists. So these both these limits exist. I can now split this into two different limits. So this is going to equal the limit as x approaches a of f of x to the kth power times the limit as x approaches a of f of x to the first power. And one thing that we've assumed about both of these, well, okay, we've assumed about the first one. The first one, we said the limit as x approaches a of f of x to the kth power can be written as the kth power of the limit. So let me go ahead and do that. Let me rewrite this first one as the kth power of the limit. And the second one also can be written as the first power of the limit, right? That was the first domino. Well, let's see. I have a number to the kth power times the same number to the first power. That is going to be that number to the k plus first power. And again, I can do this because the limit of the function exists. Now remember what we wanted to prove. We wanted to prove that the limit as x approaches a of the k plus first power of f of x is equal to the k plus first power of the limit. And look, through a chain of equalities, we have shown that this is true. This is equal to that. We have shown it's true. So what just happened? Well, we've knocked over the first domino. We said, listen, it works for 1. I know that's true. If it works for some number later on, any number we want, by the way, we've just shown that it will always work for the next one. In other words, it'll work for, if it works for k, it'll work for the k plus first. Just assume for a moment that k equals 1. That means that what we've just shown here is that it works for the next domino. In other words, the next domino will have to fall. Well, that means that it works for k equals 2, which means that the next domino will fall, because k plus 1 it'll always work for it, and so on and so forth. And that's why I call this like a domino style of proof. Of course, a proof is not complete until you state the end result, so you kind of have to just say thus or therefore or hence, whatever you want to say. The limit as x approaches a of the nth power of f of x is equal to the nth power of the limit as x approaches a for all numbers in the set of natural numbers. And by the way, probably I have some people screaming at me early on when they saw this proof. The part of the proof here, let me get back to the beginning. Part of this proof, by the way, is that this is true for all n in the natural numbers. It's not necessarily true for other n's, but it is true for all n in the natural numbers. So I should have stated that early on. And the induction hypothesis, we were only dealing with natural numbers, so that's why we've just proved it for all n in the natural numbers. Q, E, D. We are done.